Welcome back, folks. Here's another Thevenin application of Thevenin's theorem. I promised you a problem that you'd be forced to use method 3 for. Okay, my name, method 3, the third method I introduced to finding the Thevenin resistance of a circuit. So let's get at it. Okay, here it is. So look at the circuit and look at the supplies. They're all dependent supplies. Okay, they're all in diamonds, if that helps. So there is no independent supply. So I can't use method 1 because there are dependent supplies in the problem. I can't use method 2 because there are no independent supplies in the problem. So I'm left with method 3. The other thing I can tell you is, just by looking at this, I can already tell you what V Thevenin is going to be. It's going to be 0 volts. I'm going to do the analysis, but there's no independent supply to create any current IX, so that these supplies aren't going to create any current, since they're both dependent current supplies. Okay, so because there's no independent current supply, I can tell you that V open circuit, and therefore V Thevenin, is going to be 0. But let's do it at least once so that you see that that's in fact true. Okay, so let's see. Let's do the first thing first, right? And find V open circuit. So I'm just going to take that there. In order to do that, I need to do some analysis, whatever you choose. 1, 2, 3. You might be able to do nodal, but I'm gonna do mesh. I2, I3. Not much shortcut I can do here. I can use the shortcut on I2 because there's no dependent supplies there. But for I1 and I3, well, they're current supplies, so I gotta write KCLs first off, even though I'm doing mesh. And they are dependent supplies, so I'm gonna go slow and make sure I get it right. Okay, so first thing we're doing is find V open circuit. Okay, so this is the KCL for I1. Okay, and we can say, does I1 touch that? Yes, it does. And it goes in the positive direction. Does I2 touch it? Nope. Does I3 touch it? Nope. And that's all equal to 6IX. Okay, IX is a problem. We got to deal with it. It's our control variable for that supply, and we can see that IX is labeled over here. Does I1 touch IX? Nope. Does I2 touch IX? Yep. Does I3 touch IX? Yep, and it goes in the opposite direction. So there's my substitution for IX. Take that, sub it in, and then make sure you distribute that 6 to both terms. So I'm going to rewrite this equation down here. I1 equals 6I2 minus 6I3. And then I just got to get them all over on one side so that I can get it ready to stick in the matrix. Okay, so I1 minus 6I2 plus 6I3 equals 0. And there's my first equation. It wasn't too bad. Hopefully that's all becoming kind of mindless for you. Hopefully you feel like you have the tools to analyze this circuit where you didn't when you came into the class. Okay, so moving on to I2, I'm going to write a KVL for I2. I said you can use the shortcut, and we can do it in equation form. So we can say, what does I2 share with I1? Negative 30 I1. What does I2 touch? 38 and 25. So what is that? 55 and another 8. So 63. So that's going to be plus 63 I2. And then what does I2 share with I3? It shares the 25, negative 25 I3. There are no sources, so that's equal to 0. Okay. So that's our second equation. We only need one more. Let's see what it is. We have another current supply over here, and I3 is the only mesh current that touches it. No super loops in this one, which was kind of nice. KCL for I3. Ooh. You're watching this in October, but it's actually like early August. The grass pollen's just out of control. And we're getting a tropical storm today. So it should be good times. Okay. Does I1 touch this current supply? No. Does I2? Oh, they're both labeled IS. That's junk. Who wrote this thing? I did. Sorry. Okay, I don't think it matters much. Does I1 touch IS2? No, it doesn't. Does I2 touch IS2? No, it doesn't. Does I3 touch IS2? No. Yes, it does. But it goes in the opposite direction. So we can say that negative I3 is equal to 10IX. Okay, so I've been preaching about don't reuse analysis, but this is the same analysis. It's the same system of equations. I haven't changed the circuit in any way. So IX is actually the same. So I'm going to take this IX and I'm going to plug it in for that right there. Okay, let me scroll down and get some more room. Okay, and we got to do the same kind of stuff. We've got to say negative I3 is equal to 10I2 minus 10I3. Okay, and we got to move it over to the other side. So it's going to be negative 10I2, and we're going to add 10, so we're going to get plus 9I3, and that's equal to 0. And those are my three equations. Okay, solving that system of equations as quickly as possible. I just grabbed my calculator. I'm faster on this one than I am with the on-screen one. I want you to be using whatever calculator you have. Okay. Woo. Hey, watch out. There's a 0 out front here, right? So don't get tricked by that. Like I just about did, but I caught myself. Well, I did it. I wish I could show you this. Now I wish I was on screen. Maybe you can see it. This is my beat up old calculator that I bought years ago, and I still love the thing. Okay, so what we find for this solution is I1 equals 0. I2 equals, well, also 0. And I3 equals, well, also 0. Okay? What we're really interested in is the open circuit, which is over here. And, you know, if all the currents are 0, it's got to be 0, right? Well, that's probably not a horrible assumption. I can't think of a circuit off the top of my head that wouldn't be true. But let's at least think about the KVL we would have to write if that wasn't the case. I don't want to cross over this current supply, so I've got to find some other KVL that includes V open circuit. And I think the easiest one that sticks out to me right now is to write the KVL around here. Okay. And then writing that KVL, what you'd find is that this is 0 volts. This is 0 volts. This is 0 volts. And then, so if those are all 0 volts, then V open circuit has to be 0 volts, right? So V open circuit equals 0 volts. I promised you that would be true, but the analysis bears out. Oh, that's all behind my head. V open circuit. Right. Oh, my finger. Ow, my finger. Okay. The open circuit ends up being 0 volts, just like I promised. I like it when it's consistent. It's not some goofy rule that I just said like, hey, there's no independent currents, no independent supply. It's always going to be 0 volts. If you go through and you do the analysis and you follow all the laws, it's going to be 0 volts. Okay. All right. That's not the tough part. I mean, this next part's not even that bad. It's the same stuff just over again. We got to go find our Thevenin. Oops. Okay, and if we're going to go find our Thevenin, we've got to use the third method I introduced. All right, so let me get a copy of the circuit. I'll stick it over here. And we have to remove the load if it's drawn. In this case, it wasn't. This is one of the ones that says, hey, we're going to put the load between A and B. So the load's already removed. We have to turn off all independent sources and replace them with their ideal resistances. There are no independent sources in this problem. We need to drop a new voltage supply where the load would be connected. And then we need to find the current through that new voltage supply. So here's my on-screen emulator. I'm going to pick a random number. I would usually have you pick this random number. You're not here. I don't even know you yet. I look forward to that. I do. So let's, I don't know, what do you want to, let's go from 1 to 10. You could make it up to 1,000 or some goofy stuff, but I don't know. I like keeping my numbers round, at least for now, but let's see what the circuit does to it. Let's do steps of 1. So random number between 1 and 10, steps of 1, and we got 10. It is what it is. Let's go with 10. I promised you I would use it. There it is. 10 volts. So we got to figure out what current flows here if I apply 10 volts there, and that's going to give us the equivalent resistance, which is kind of nice. Okay. I1, I2, I3, I4. Okay. We got a fourth mesh. That's why I drew that yellow dotted line, right? Build that firewall. Don't use any of the analysis from up above. You're going to get yourself in trouble. And then I'm going to have to give you a bad grade, and nobody likes that. Not even me, believe it or not. All right, so 2 current supplies. So we're going to write 2 KCLs. Ooh, now we have a super loop. So we got to handle that correctly too. Let's get at it. KCL for I1. We've got I1 is the only current that touches this, and it goes in the positive direction. So we've got I1 equals 6IX. IX equals I2 minus I3. I1 equals 6I2 minus 6I3. Bring all that over. I1 equals minus 6I2 plus 6I3 equals 0. Okay. Is that the same? It might actually... It sometimes ends up the same. Don't let that lull you into a false sense of security. You can get yourself in trouble. Okay. KCL... Ooh, not KCL. KVL for I2 around the I2 mesh. We have negative 30 I1. We have 63 I2. And we have negative 25 I3. And that's equal to 0. Okay, so there's my second equation. That one might even end up the same. Hold on a second. And now we get into here are the differences. Work the steps. Just don't screw up because you're being lazy. I fully encourage you to be lazy. I just be lazy and get it right. And I think being lazy in this case brings trouble. So this is the KCL for the super. Should really write that it's I3 and I4 because you can have 2 different super loops in a problem. It happens. So this one's I3 and I4. It's the only super loop in this problem. Okay, so for the KCL, I3 touches it, it goes in the opposite direction. Am I behind me? Nope. I3, I4 touches it, it goes in the positive direction, and that's all equal to 10IX. It's the same IX as long as I stay within the same problem. So I can use this, and I can plug it in over there. So we get negative I3 plus I4 equals 10I2 minus 10 I3. Okay. We got to pull those over here. So we got negative 10 I2, positive 10. So we get plus 9 I3 and plus I4. And that's equal to 0. Even the long way, I try to move as quick as I can while still getting it right. Okay, the super KVL. So I got to go around here. Believe it or not, I can use a shortcut on this one. If you're comfortable using the shortcut on super loops, we can pull this off. We're a bunch of smart people. We're well educated. Hopefully. So what does the super loop share with I1? Nothing. What does the super loop share with I2? It shares the 25. So it's going to be negative 25 I2. I got to do some scrolling. I'm sorry. So let's say this is the super KVL, negative 25 I2. What does the super loop touch that? What does it share with I3? What does the green share with the I3 mesh? It only shares the 10. Right? We don't cross over the 6 if we're going around this way. So, and it's on the super loop, so it's positive. So it's plus 10 I3. Okay, what does the super loop share with I4? It only shares this 4 ohm here, so it's plus 4 I4. That's a lot of 4s. Plus 4 I4. Okay, right-hand side is any sources. So it looks like we go down across the 10 volt, so it's going to be negative 10. Okay, so shortcut still works. It was a little quicker because of that, but you got to remember what questions to ask yourself. All right, we got to solve it. I'll pause for you, okay, and I'll come back with the answer. Okay, so there's the solution. I just popped it up over there. I made some mistakes while I was doing it. You got to be real careful. So this has I1, I2, I3. There is no I4. This one has no I4. So there's those hidden coefficients that have zeros. This one has no I1. This one has no I1. So just be careful when you're entering it that you get all the coefficients in the right place. Okay, now I new is over here. Oh, we're going to end up with a negative. Ugh, yuck. These current supplies are pushing it the other way. And let's see, so I1 doesn't touch it, I2 doesn't touch it, I3 doesn't touch it, I4 touches it but goes in the opposite direction. Let me just see that I didn't miss a sign. These current supplies end up pushing that current the opposite direction. So I new is equal to negative I4, which is equal to negative 6.93 amps. Okay, so the resistance for Thevenin, here's the payoff, is equal to V new over I new. Okay, so it's going to be 10 volts over, I didn't leave myself enough room, over negative 6.93. Well, this thing's going to end up being active. It's got those dependent supplies in it. So really the negative sign tells us that something silly is going on here. We've got some amplifiers. There's certainly some gain involved in the circuit. I'm comfortable with you talking about the resistance as the absolute value in this case. And let's see, 10 divided by negative 6.93, and that's going to give us, I'm going to take the absolute value, 1.44 ohms. Okay? It'd be fun if we could actually hook this one up. That'd be great. But there's your Thevenin resistance. You have to use method 3, and goofy things can happen. Okay, so I think I've given you examples of every method of finding our Thevenin. This is going to come in real handy when we go learn Norton. I want to take one step back. I want to look at a bigger, more complex circuit. I want to break it in two. Okay, the load isn't always a single resistor. Sometimes the load is another circuit. And we can think of that load as another Thevenin equivalent. So I want to give you an example of that. That's what's coming next. And then we'll do probably move on to Norton and something called maximum power transfer theorem. So if that doesn't get you excited, I don't know what does. Stay tuned and good luck, folks.